velocity. If we started it moving backwards, let's see. Well, there's really no way I can make it stop at the end. Yeah, so it'll be moving when we're done. Right. Yeah, that's, yeah. Well, so the question is, if it's moving faster, why doesn't that change the work done? Because it does not change the kinetic energy, it changes the change in kinetic energy. The answer is no. If it starts at rest, it will accelerate to some speed, and the change in kinetic energy will be its final kinetic energy, because the initial kinetic energy is 0. So maybe it starts with 0 kinetic energy and ends with 2 joules of kinetic energy. If I throw it so that it starts with 10 joules of kinetic energy, then it'll end with 12 joules of kinetic energy. If I throw it harder so that it starts with 20 joules of kinetic energy, it'll end with 22 joules of kinetic energy. No matter what speed it moves, the increase in kinetic energy will be the same 2 joules in that example. Okay, you had a question?
Because I'd actually like to hear this too.
Oh, good question. How does it move faster if it's in a static force field? Because I threw it into the field. And so it's an initial condition that I could give you. I could place it gently in the field, let it go, and then it starts at rest, and it accelerates purely by the field. Or I could throw it into point A from, say, left to right, and now it starts out at point A already moving with some speed, and it still gets accelerated by the force. Okay? Other questions? Yeah.
But you said the field can never accelerate the particle, but I would say that assuming the field is uniform.
Wait, the field cannot accelerate a particle?
Yeah.
No, absolutely it does. It exerts a force on the particle. Field accelerates.
But the acceleration is uniform, you said.
No, it depends on the force field. In a spring, for example, the force is stronger the more it's compressed. And so if I compress the spring and let it go, the particle accelerates quickly at first, and then it accelerates more slowly later on. Its speed is always increasing, but its acceleration is actually decreasing as the spring relaxes and its force gets weaker and weaker. Okay. So a particle always accelerates under a force field, but the magnitude of the acceleration is proportional to the magnitude of the force field. And as the particle moves through the field, the magnitude of the force field that will change, or it could change. Okay? All right, great questions. Oh, we just did that. I was going to say, wow, this really fun. Okay, so now we can define potential energy more completely. We define that change in potential energy is equal to the potential energy at some final position, which we call B, minus the potential energy at some initial position that we call A. And we said that that's the negative of the integral of the force, which may be a function of x dx in one dimension. But that only defines changes in potential energy between 2 points. So how do I define a potential energy field U, which is a function of position? Easy. I pick some point that we all agree on, and I say that's my reference point, and I will arbitrarily call that the point of 0 potential energy. And then I measure all of my potential energies relative to that reference point. So for example, I might say that the floor is the reference point for gravity, but there's actually a room underneath this room. Somebody down there might not like my choice of this floor as the 0 point for potential energy. So I would say this book has 0 gravitational potential energy. Now it has gravitational potential energy because I lifted it off the floor. The guy downstairs might want to say, well, no, it started out 12 feet off my floor. Maybe it started out with potential energy. And that's fine. He's totally allowed to do that because none of the physics will change. I can say, look, I'm tired of stooping down to the floor. I actually want to use this desk as my 0 point. And so now before I said this book has potential energy, now it doesn't. It's not that the physics has changed, I've just changed my reference point. And we will see that since the force is proportional to the derivative, or the gradient of the potential energy, any additive constant in the potential energy has no effect on the forces. And so they are equivalent potential energies. And in general, we will find this is true all the way to the end of, almost to the end of physics. That an additive constant in your potential energy is totally legitimate, has no effect on the physics, and you can choose your reference point for the maximum convenience. Right? And we do that in problems. We pick the most convenient reference point we can. Often that means the starting configuration of some system is 0. Not always, but often. Sometimes we make the ending configuration be 0 potential energy. But we have that freedom to choose that. So that's what I mean here. This is how we get an absolute scalar field, a scalar function of position, out of changes in potential energy. We just fix one point and call it 0. And then we can see that, based on that little line integral, the potential energy is F dotted into dx. In one dimension, it's F times dx. Therefore, the change in potential energy per unit x is the force. And if I do that over an infinitesimally small distance, that's called a derivative. It's the definition of a derivative. So in one dimension, f of x is the partial derivative of u with respect to x with the ever-present minus sign. That just means that when the work done is positive, the potential energy is going down. When the work done by the field is positive, the potential energy goes down. In 3 dimensions, we use the gradient operator, which is just a derivative with respect to x in the x direction, plus a derivative with respect to y in the y direction, and a derivative with respect to z in the z direction. The gradient produces a vector field out of a scalar field. We start with a scalar function of position and we end up with a vector function of position. That's what the gradient operator does. Okay? And the ever-present minus sign. Is that clear? No? Okay, I appreciate your honesty. Does someone want to ask a question about it to help me figure out what's not clear?
What's that, the upside down delta symbol?
Oh, this is called it's often called grad.
Grad.
But it's also called a nabla, which is like Norwegian or something. You know, I don't really know, but nobody in physics calls it nabla.
Oh.
But it's usually it's sometimes called del, like del U.
Del.
But it's not a delta. Delta is right side up.
Okay.
It's upside down. It's a very different. Right, but the gradient operator is just short for these 3 derivatives in the x, y, and z direction. That's how you make a vector out of a scalar field. Okay. Yeah. Hold on. Somebody up here had a question. Somebody. Yeah.
It's okay. I had the same question.
Oh, okay. Yeah, you have a question.
So does that mean that no derivative actually, so this basically means that the force is unable to change the potential energy, but in a specific direction. So
Yeah.
that's the more broader definition of force.
Well, force is a vector. So the question is, in 3 dimensions, it means the force is given by the derivative of the potential, but in a specific direction. But in 3 dimensions, force is always a vector. It's always in a given direction. And this is how we get a full vector with magnitude and direction out of the scalar that has no direction, only magnitude. When you take its gradient, you get 3 derivative operators and you associate them with the x, y, and z components of the final vector. Okay, we have 2 minutes to go. Any other questions on this? Yeah.
So no problem if they gave you u, if you would do the derivative to get the force, or if they give you the force, you would do the integral to get the u.
Yeah, so the question is, like in a problem, if they gave you a u and you needed the force, you would take this gradient. And on the flip side, if they gave you some force field and asked you for the work, or asked you for the change in potential energy, which is essentially the same thing, so we get a minus sign, then you would do the line integral that I mentioned. The f dot dr is the line integral. And that would give you the work or the change in potential energy. Okay? Anything else? Okay, so as an example, we'll start this example now, we'll finish it next time. The gravitational potential energy of a point mass So a point mass is something we can consider as being all mass concentrated into a single point. Say the Earth, right? The Earth isn't too big. But it turns out we actually can consider all the mass of the Earth to be concentrated at a single point. I won't bother proving that to you because it's a little tedious. But trust me on this one. And if I'm in a spaceship going to the moon, say, to set up the retroreflectors for my lunar laser ranging experiment, I can treat the Earth as a point mass. And my potential energy relative to the Earth means a lot to me. Because if my potential energy, because that affects my trajectory, that affects whether I can come home or not. If my kinetic energy exceeds my negative potential energy, I ain't never coming back. I'm going to just shoot out into space and that's it, so long. So I would want to know this. If I work at NASA, I need to make sure that my spaceship stays within the gravitational potential of the Earth, because I want those people to come back. So we can do this calculation using a one-dimensional analysis by just following a radius straight out from the center of the Earth. And we'll do that next time. Thank you for your attention.